Welcome, welcome. Hope everyone is doing well this week and everybody had a good weekend. We are only a couple weeks away here from the end. So we're going to keep moving forward, get through this content, hopefully prepare you well for the final exam and for any other chemistry related activity you may end up involved in. So continuing where we left off with chapter 22, which is about enolates. There's some variations on the aldol reaction that we talked about that are relevant and worth mentioning. One is the so-called Claisen condensation. And in the Claisen condensation, you're starting with an ester specifically. Right? The ester functional group has a CO double bond and an OR. And what's special about this versus the aldehyde or ketone functional groups that we were looking at working with last time is that the ester has a leaving group. Neither of these have a leaving group. So if an enolate were to attack them, remember the enolate is stabilized by resonance. The major resonance contributor has a negative on the oxygen. The enolate has to come in here and push electrons up, and then those electrons stay on that oxygen until a proton source is added, and it turns it into an OH, and then it may be heated to undergo a subsequent elimination reaction. We talked about that. But with the ester, what we see is something a little bit different. So if we explore that, first step would be the same. We still have to make an enolate. So we'd put some kind of base in there, something strong enough to pick off an alpha proton, alpha to the carbonyl, to make an enolate. And again, since this is stabilized by resonance, the major contributor puts a negative on the oxygen. But normally the carbon that attacks, because that maintains a CO double bond, which is more stable than the CC double bond that exists when the electrons come in here and form a double bond, and we imagine the negative on the oxygen. So we expect this enolate to attack, which it should, and the second step is basically the same as well as what we were seeing last week, where the nucleophile attacks the carbonyl carbon, which pushes electrons up to create a negative. The main difference here, though, is now there's a leaving group. So the next step we expect to see is one of these lone pairs shifting in and pushing out that leaving group. And that would result in this structure here. The leaving group that left is not a great leaving group. It's not especially stable with a negative. It's still a strong base. And now that we've connected these two compounds together and we have a proton that's alpha to two CO double bonds, this base is going to very quickly and very much in a product favored way pick up this proton to put the negative at a site where it can be stabilized now over three atoms, two of which are oxygens, and so the majority of the negative spread out over two oxygens, definitely going to be a lot more stable than stuck on one oxygen with no resonance at all like we have here. So once this leaving group leaves, it's now a base. And it's going to pick up the alpha proton that's alpha to both carbonyls. It's not going to pick up this one because the resonance would be much less significant with sharing the negative over only one oxygen. So it picks up the proton that's alpha to both carbonyls, and that step is pretty much only product favored. So when this last step reaches equilibrium, there's going to be virtually none of the negative charge on the oxygen that can't stabilize that through resonance versus the other one. That's what drives this process forward. So once we get to this point, all the molecules accumulate into this form, because it's way more stable with the extra resonance than anything we started with. And then if we want to remove this charge altogether, we would just have to add some H3O plus, some acidic product source in a second step. Right? We can't add it before, otherwise it will just protonate all the negative charges that we're using to get to this product. But that would protonate this, right? So obviously this negative charge pick up a proton, and you would produce a product that looks like this. So what's nice about this is it provides us with a new functional group. We get 2 CO double bonds, not on adjacent carbons, but 3 carbons away from one another. And that, it's not really a new functional group, but it's a new connectivity or arrangement of the atoms that we haven't really previously seen a way to form. So here we're saying the resulting doubly stabilized enolate, that's this one here, that's what drives that forward. We need a proton source to protonate that in the last step because it's well stabilized otherwise. And we have something called a beta keto ester. Right, so here's an ester. This is the carbonyl carbon. Here's the alpha, and here's the beta. So we have a keto or ketone functional group beta to the carbonyl of this ester, or a beta keto ester. All right, so some limitations on this reaction you should be aware of. One, you have to have at least 2 protons on the ester. All right, so let's go back and take a look at why that is. So here's my original ester. I have 3 protons here on this alpha carbon to begin with. I need at least 2. Right, so let's imagine what it would be like if we didn't have that. So let's say maybe the carbon alpha, obviously if there's no proton here, we can't even start the process off and make an enolate. But what if we had a couple methyl groups and 1 proton? Oh, the base would still pick off that proton. And so I could make an enolate. Then that could attack another molecule of the ester that hadn't yet formed into an enolate. Then, just like up here, those electrons swing back down and push out the leaving group. So now, this carbon here, which is this one, now it just attacked the carbonyl carbon. So now it's connected to that carbon. When those electrons swing up and then back down and push out the leaving group, when they swing back down, it reforms a CO double bond. So we'd have that. So at this point, the leaving group that left right here is also negative, and that's pretty unstable. So normally that picks off a proton from this alpha carbon. That's why we need a second proton here. If there's no other protons here, because there's only 1 to begin with, and that was removed to form the enolate, what this is going to do, because it's not stabilized by resonance, fairly unstable still, is it's going to come back in and push electrons up. And then once in a while, they'll swing back down and push this guy back out, and we'll go back. And so we really have no way to force the equilibrium forward. We're starting with a relatively unstable negative. We're forming a relatively unstable negative. We don't have a way to really favor the equilibrium on one side or the other, so we can't really form a very high yield of the product. All right, so we need the second proton to be here so that that leaving group can pick it up and form a much more stable product. And then that last step is what drives the whole equilibrium forward by Le Chatelier's principle, right? If I'm removing the product of the most recent step and converting into something a lot more stable, and that step only goes forward, then every time a little bit of this forms, it'll continue to react forward, and that will draw everything forward eventually, right? So that this is a key point. Picking off a remaining proton is what drives this process forward, and so we have to have 2 total protons or more. I should say it must have at least 2 protons. That way, the second proton can be picked off to push that equilibrium forward. The other limitation is we can't use hydroxide as a base, and that's what we've been using a lot last week. The reason for that is because the hydroxide can attack the ester and hydrolyze it, right? So if we're starting with some ester here, we might have an R group. We can't have more than 1 though, because we need to have at least 2 protons here for this to work. So the if we use an OR, an ethoxide as a base, that's fine, because the ethoxide or some other alkoxide, it can do what we want it to do, which is to pick off this proton and make the enolate, or it could come in here and attack. And if the electrons swing back down, it doesn't matter really which OR groups gets pushed out because they'd be identical. So this side reaction where the alkoxide attacks directly isn't an issue, because if it happens, the electrons get pushed up. When they swing back down, either one of these, since they're identical, can leave, and we're right back where we started. And then in that case, instead of doing this, once in a while it can come here and make the enolate and then go through the mechanism we just saw. However, with hydroxide, that's a problem, because if I have a hydroxide, it will react with the ester. And we know, if you recall from last week, adding hydroxide is a way to cleave an ester, because the hydroxide will come in here. Once in a while, it might pick off a beta proton and initiate the reaction we want, but a lot of times it'll come directly into the carbonyl because there's a very large partial positive here, push these electrons up, and then when they swing back down, it'll push out this leaving group. So the OH will replace that OR leaving group. And then you might think, well, what's the problem? That could come back in and go back, but the problem is that OR leaving group is mostly going to act as a base now and pick off this proton. And now the resonance stabilized carboxylate that results is going to drive that process forward. So even though this might be in equilibrium, this step here can't really go back. So if you add a hydroxide to an ester, you can expect hydrolysis to occur, which involves the hydroxide attacking, pushing electrons up. Those electrons swing back down, push out the OR leaving group. Then a deprotonation occurs to produce a resonance stabilized carboxylate there. So that's issue 2. If you want to do this reaction, you need an OR, not an OH, as your base, which isn't that big of a limitation. I mean, we can buy that, no problem. And then limitation number 3 is similar to 2. It has to do with the same type of issue. And that is just whatever OR group we have here on the ester, whatever this R group is, we want to use the same R group on our base. That way, if it does come in here and replace the other group, there's no difference because the R groups are identical, right? If you want to have an ethyl group here, you wouldn't want a propyl group on your base, because then the O with the propyl will end up replacing the O with the ethyl sometimes, and you'll get a mixture of products. Some of the products will have an ethyl here, some will have a propyl. That's no good. We want a clean yield a product, so just want to make sure the R groups here are the same. This R group can be anything, so we'll just call this R prime. So this R group could be anything, but these two, you want to set it up so they're the same R group. So that was a Claisen condensation. And just one other point here. You want to note that in this Claisen condensation, the first molecule of the ester that we started with becomes an enolate, and then it reacts with another molecule of the ester that's identical, right? So these two structures are the same. And when that's the case, this works well because, as we've been talking about last time, an alkoxide base isn't strong enough to convert 100% of this into the enolate, which we wouldn't want anyway in this case. It's only strong enough to convert some of the initial ester into the enolate, which is good because if some of it gets converted to the enolate, then others molecules of the initial ester remain for the enolate to attack. Right? So if we want to do this reaction in this way, this molecule and this molecule have to be the same because or some portion of the reactants are converted into enolate, and then they attack the other portion of the reactant that didn't get converted to an enolate. But what if we want to convert one into an enolate and have it attack a totally different ester? Well, that would be called a crossed Claisen condensation because we would be crossing two different esters together instead of having one ester attack another molecule of the same ester. So to do that, we can employ the same types of strategies we looked at last week, and there were two of those. One is to use an ester with another ester and just set up where one of those esters has no alpha protons. Right? So there's no consideration here or worry that the base will pick off an alpha proton from this and make it into an enolate because it doesn't have an alpha proton. The only role this can play is as an electrophile. And there's only one site where there's alpha protons, so there's no question about how this reaction is going to go down. I mean, if the OR attacks here, it might replace the other OR, but since they're identical anyway, which is what we just talked about, that doesn't really matter. So instead, once in a while, it can come down here and pick off this proton. And since there's only one enolate that can form, we don't have to worry about multiple possible products forming. That enolate's going to attack here, push the electrons up. When they swing back down, it'll push out the OR group. That'll give me this, but there will actually be two protons here. And then the OR group that left will pick off one of those, and I'll have a negative here, and that will be stabilized through the extra resonance. And then later an acid would be used to protonate this spot to make the molecule neutral. Right, so one strategy is setting it up so there's only one site that has alpha protons, so we know for sure which molecule is going to be the enolate, which molecule is going to be the electrophile, and how the attack is going to occur. The other strategy is to add the two substances in separate steps. Right, so here I've got one molecule that has alpha protons that could act as an enolate. And I've got another molecule that has alpha protons that could act as an enolate. So if I started with them together, then I don't know which one the base is going to attack. It might attack this one sometimes and this one sometimes, and I'm going to get both converted into enolates, and then they'll start attacking one another, and I'll get a mess of products. Because if this one's an enolate and it attacks this carbonyl, I get a different product, versus if this one's an enolate and it attacks this carbonyl, since the molecules are not identical. So the idea here is whichever one of these two I want to attack the other, whichever one I want to be an enolate, I'd start with that, add an especially strong base. We talked about LDA, it looks like this. There's a full negative on that nitrogen. It's much less stable than negative on an oxygen or on a molecule where the negative is spread out between an oxygen and a carbon, like an enolate. So this is going to react basically 100%. It's so strong, every molecule of the first thing I put it in with, it's going to deprotonate to make the enolate. Then, after all of those molecules have been converted into that, using the LDA, then in a second step, you add the other ester you wanted to attack. So this would come in here and push those electrons up, and when they swing back down, it would push out the leaving group. And so that would produce this structure, which would be then deprotonated by the leaving group. So we would need a third step where we add some kind of acid to put that proton back on there and get that product. So we can have one ester attack another, and whichever one's attacked loses its OR group as a leaving group. But we have to set it up in this stepwise fashion so we know for sure which one's the enolate and which one is attacking which. You can also do a Claisen condensation intramolecularly, which means that you're forming an enolate and it's reaching around and attacking another part of the same molecule. Right? So here I've got this symmetrical ester. I've got an alpha carbon here on carbon 2 and one on carbon 5. Either one of those has 2 protons, and either one, any one of those 4 protons could be removed by this base. Notice the base. I'm selecting a base that has the same R group as the R groups that were on my ester. That way, if the base attacks the carbonyl and pushes out this OET, it's a new OET replacing it, so there's no net change in the structure. So that way I don't have to worry about that side reaction altering the structure in any way. Instead, the OET would come in here, pick off the proton. What that would give would be an enolate here, and that negative would then be able to attack here because it's only 1, 2, 3, 4, 5 atoms away. And so we often see atoms, if I have a nucleophilic site and an electrophilic site, if they're 5 or 6 atoms away, then that collision will occur fairly often without creating much angle strain or ring strain during the transition state. And so that reaction can readily happen. It doesn't require some other molecule to come in and collide with it. It can collide with anything to provide the energy necessary for it to collide basically with itself. It just has to rotate. You know, these bonds have to rotate to allow carbon 1 and carbon 5 here to be close enough together. So if I asked you to draw that transition state, it would look something like this. You would have the OET. What would be happening is, as this attacks, one of these pairs of electrons will swing out there, so we'd want to show that pair of electrons moving out. And actually this shouldn't be here because that is that pair of electrons represented with the dotted line. So there'd be the other carbons in the chain. And then this carbon with its lone pair of electrons would attack there, and that would start forming a bond. Oops, scratch that. It would look like this. Nope, I made a mistake there. Not enough space. Let me draw that again. Can't really erase with this PowerPoint, unfortunately. All right, so we have carbon, so we'll keep this numbering system too. So this would be carbon 6. And the oxygen there would start to pull electrons out to become a negative. Carbon 6 still has an OET. It's got carbon 5, 4, 3, and 2 is the alpha carbon. So carbon 2 collides with carbon 6. That's where the new sigma bond is forming, and carbon 2 will take on a partial negative as its formal negative from the enolate will start attacking there and being diminished. And then so carbon 2 is bonded to carbon 1, and that would be the other ester. All right, there we go. So that's, and this, the angles here wouldn't preclude the attack because the angle strain would be minimal. Once that attack occurs, the electrons will swim back down and push out this OET group, which is why we don't end up with an OET group on carbon 6 anymore. That OET leaving group would be negative. It would pick off the remaining proton from carbon 2, and then that's why we need the acid in a second step to put that proton back on. So you want to be aware of and do a little practice with these cyclic Claisen condensations as well. So let's look at a couple more examples here of the Claisen. What's going to happen here? What do we got going on here? Well, this looks like a cyclic one, just like the last one, because I'm forming a ring. And retrosynthetically, what I'm noticing is that this is the bond that must have formed. Right? I'm looking for a bond between a alpha carbon to an ester group and a carbonyl. Right? What we formed here, as we said, is a beta keto ester. So this is my ester. This is the alpha carbon to that ester, and this is the beta carbon. I've got a ketone on the beta carbon. And so when I see a beta keto ester formed as my product, I realize it's going to be the alpha carbon of this ester that attacks the other one. And normally when that attack occurs, electrons will swing up. So for them to swing back down, there must have also been a leaving group there. So let's number these carbons here. 1, 2, 3, 4, 5, 6, 7. We'll just number the main carbons involved in the reaction. So really I need to get carbon 2 to attack carbon 7, and carbon 7 must have had a leaving group. So the original structure that I would have wanted to use to make this ring would have had carbon 1 with its terp-butoxy group attached to it as an ester. So that would be bonded to 2, 3, 4, 5, 6, 7, and 7. So 6 has a couple methyl groups, and 7 would have had to have been an ester. And I would want to use the terp-butoxy so that I can use the terp-butoxy base. Right? That way, I keep all my OR groups on my ester the same and make them the same as the base. That way, if the base does come into the carbonyl and push out the OR group, it just replaces it with an identical OR group, so there's no change. Right? So what would happen in the forward direction here is it would be these protons here on carbon 2, which is the carbon we said we wanted to connect to 7. So this base would pick off one of those protons, make an enolate, then the enolate would attack 7, push electrons up, they'd swing back down, and that would push out this leaving group and give me this product. The leaving group would then pick off this last remaining alpha proton, so in a second step, I would need some H3O plus to return that proton onto carbon 2. For the second compound, I see the same feature. I see an ester, I see the alpha carbon to the ester, and the beta. So I have a beta keto ester. And again, it's the alpha to the beta bond that we're forming in this reaction. So this is where I'm going to disconnect retrosynthetically. I'm going to start with a piece that's separate on this side of the disconnect, and then the other piece on the other side of the disconnect, and I've got to get this carbon to bond to that one, which is the same as getting this one to bond to that one. Right? So the idea here is I would start with this ester, make this carbon here into an enolate by adding a base. What base do I want to use? I want to use an ethoxide in this case, just in case the base comes in to replace the OR group. I still get the same OR group back. That will make an enolate here, and it will attack here, but there has to be a leaving group, so I'm going to put an ethoxide group there. That way, if the base attacks here and pushes that ethoxide group out, I still get no change in the structure. The only change in the structure would occur when this alpha proton is picked off by the base. That'll make an enolate here, and when the enolate then attacks to push electrons up, they'll swing back down and push out this leaving group. That will make the product, except for it would then be deprotonated, so I need the H3O plus to reprotonate it. So if you have any questions about any of that, let me know. So we've talked about the aldol, the version of the aldol that occurs when you have a ketone instead of an aldehyde. We've talked about the Claisen condensation. Another important reaction that works well with these enolates is an alkylation of the alpha carbon. Right, so an alkylation just means you're adding an alkyl group. It's just an R group. So this is pretty straightforward. I'm using a strong base to pick off this proton. So LDA would definitely do the trick. I need a strong base because I need to convert all of these molecules into the enolate. I can't leave any behind. If any of them don't get converted into the enolate, then the enolate may attack the ones that didn't react and that are remaining. So I need an especially strong base with a really unstable negative compared to the unstable negative that's going to form to pick off that proton and form the enolate. And so once that occurs in a product only direction, because this is such a strong base, it's so unstable, when I look at the pKa values of its conjugate versus the original compound, the conjugate acid of this base has a much higher pKa than the original pKa. I think this one's on the order of about 35 versus about 15 to 20 here. So this is pretty much only product favored. Once it forms, then in the second step, I'm going to add an electrophile with the leaving group. The limitation here is this must be a primary carbon that the leaving group's attached to. And so if it's a secondary carbon that the leaving group, just put Lg here for leaving group. If I put a leaving group on a secondary carbon, there's too much sterics, and what will happen is this will end up doing an E2 elimination instead of the SN2 backside attack that pushes out the leaving group and adds an R group to that site. All right, we don't want to pick up a proton, add a proton to that site, because we already had a proton there to begin with. That doesn't achieve anything. All right, we're trying to add an R group to this alpha carbon to further the complexity of the carbon skeleton and build up our structure into something specific. So we make an enolate and add a primary alkyl bromide or chloride or iodide so that that can attack it and push out a nice stable leaving group. And that leaving group, being a bromide, chloride, or iodide, is going to be way more stable with the negative than the carbon-oxygen resonance combination, or especially the negative charge on the nitrogen. So each one of those steps is very product favored because we're starting with a very unstable negative and making it a little bit more stable, well, significantly more stable each time the step occurs. And so, as we said, you can't use a secondary or tertiary alkyl halide because the enolate would more often attack as a base and do an E2 mechanism, which we just showed on the last slide. The aldol also competes with the desired alkylation, and we mentioned that, right? So just to reiterate that, this is why you need a strong base. You need a base that will convert every one of these initial reactants into an enolate. If you use a weaker base and only a fraction are converted to the enolate and then some react back and you end up with an equilibrium where you have some of this and some of this, then this will start attacking the other one. And if you're trying to make that happen, that's fine. But if you're trying to just connect an R group here, we don't want that. We want all the molecules converted into an enolate, and then we'll add the R group for them to attack with the leaving group attached. Regio selectivity is an issue here. What do we mean by that is, it wasn't really an issue here. Let me just get rid of some of this clutter so I can make that point. Because in this structure, it's a symmetrical molecule. So if the LDA pulls off this proton, or this one, or this one, or this one, I get the same enolate either way, right? Even if I drew the enolate like this, obviously it's the same as this, just flipped over like a pancake. Those are equivalent. So it doesn't matter which side the enolate forms if the structure is symmetrical. But sometimes the structure might not be symmetrical, like this one. Here, I have an R group on one side and not the other. So here I've got a proton, and here I've got two protons. So we want to think about and talk about how to control which enolate forms. Because if this proton is removed, we would get this enolate, and this would attack, if we're doing this alkylation reaction, this would be the first step. We would add LDA, potentially, or some other strong base. That would then attack the R group and kick out the leaving group. And I would end up with an R group on this carbon and one that was initially there, so there's also an R group on that carbon. If my base picks off the other proton, then I get a different enolate. So if it picks off the proton on the carbon where there was an R group, then that would pick up another R group through this alkylation process, and you would end up with two R groups on the same carbon, which is obviously a different product than if I have one on each carbon. So we want to make sure that if we can control this, we control it and make sure that the product forms with the R group connecting to the specific carbon where we want to connect it. And so we'll have to describe and discuss how to do that. So there are two different, if you have a carbonyl with two non-equivalent alpha carbons, each of which has a proton, picking off one proton often gives a so-called thermodynamic enolate. Picking off the other proton gives a so-called kinetic enolate. And usually the thermodynamic enolate is more stable because it's more substituted, meaning that the pi bond has more carbons connected to it to stabilize it. And so it's more stable. The kinetic enolate is less stable, but it goes through a lower energy transition state specifically because the bulky R group would create steric hindrance when the base, especially if it's bulky, comes in to try to pull off this proton. So if the proton is surrounded by large R groups, the steric hindrance that occurs during the transition state means that this won't happen as often, or I should say this one won't happen as often because of the sterics required to pull off that proton. So instead, the base would be maybe more likely to go for the proton where there isn't any R groups around to block it out, so the transition state will be lower energy because there won't be steric repulsion occurring during that transition state to form the enolate on the other side. So here's the energy diagram that describes that. And it's a little bit exaggerated here to make the point, but it's enough of a difference here where you can control to a pretty large extent which enolate forms, and then once you know which enolate forms, you can get that to connect to an R group on the side that you want it to connect on, right? Because this enolate would swing electrons down and attack an R group with the leaving group and end up producing a product that would have R groups on both sides. Whereas this one has the enolate on the other side, so when the electrons swing back in, this pi bond would reach out to an R group with the leaving group there, and that would give both R groups on the same side, right? So different products. Obviously, if I want to form one and not the other, I want to be able to control this. So the way we control it is by selecting a specific base. And that's one of the reasons why LDA is specifically designed to have these bulky isopropyl groups on it. These large groups make LDA sterically hindering enough that we can pretty much rely on it to avoid this higher energy pathway that would occur with all the steric hindrance. Right? So if I have a proton here the LDA would have to come in and pick off that proton. These electrons would swing in here, push up to the oxygen. And if the R group is bulky, and I've got bulkiness here, for the LDA to get in there close enough, there's going to be some steric hindrance that occurs between these R groups. And since LDA is so sterically bulky with these isopropyl groups, that steric hindrance is going to be pretty unstable during the transition state. So we don't expect that to happen. And the product we'll get will be the one that happens more often through a lower energy transition state, even though it's not as stable once it forms, because the pi bond's not as substitute with R groups as it would be on the other side. If instead of using this strong bulky base, you use a much smaller base that's also quite strong, like a hydride, sodium hydride or something like that. So this is obviously very small. So if it comes in to pick off this proton, being so small with no massive R groups, there's going to be very little steric hindrance that occurs there. So in that case, the other enolate is not going to be very high in energy during that collision, right? If there's no sterics during the collision, why would it be that much higher in energy? It wouldn't be. So that means when I use a much smaller base, it can still go for either proton. If it goes for this proton, the enolate will start to form here, which is starting to form a more stable pi bond. So that actually changes the pathway to a lower energy pathway, because we're avoiding the steric hindrance and the repulsion that would occur between a large bulky molecule and these large R groups. And so then we actually end up getting the more stable product because it forms more often, because as it forms, the pi bond starts to form in a site that's more substituted with carbon groups versus less substituted. And in addition, this is not quite as strong as LDA, and this especially applies if I use an OR or OH. Since these bases are not that strong, they're actually going to form an equilibrium. So even if there's a very minimal difference between the pathways here, or even if this pathway is higher in energy, if I use a weaker base compared to LDA specifically, then the reaction can shift back and forth. And eventually, when it shifts back and forth, I have thermodynamic control, because thermodynamically, I'll end up with more of the enolate that's more stable in the end. So with a smaller, less bulky base that's a little bit weaker, the pathway for forming the more stable enolate isn't so dramatically high, because there's not so much steric hindrance during that formation of the enolate. And once it's formed, it's more stable. So if it does shift back and forth, and once in a while I get the one that forms maybe a little more often, it'll shift back and forth. And eventually that shifting back and forth will result in the majority of the molecules being converted into the more stable, thermodynamically favored enolate, which would then attack after the Rx is added in a second step. It would attack and make sure the R group gets added to that side. So I can control which side of the structure the enolate forms based on the identity of the base that I use. And so this is illustrating that. And if I want the enolate to form over here, where it's less sterically hindered, I make sure I use a very sterically hindered base so it won't come into the other side as often because of all the steric hindrance that would occur on that side. And then once I form the enolate on this side, the Rx, the enolate, will attack the R group and it will end up connected to that side. If I use a weaker base that can actually shift back and forth in equilibrium and isn't especially sterically hindered, it will pick off the proton from the more substituted side, not because it's more substituted, but because when the electrons start to swing in there during the transition state, the pi bond needs to swing up. The pi bond that forms here is more stable with more carbon groups connected to it. And so the enolate will form on that side. Once it reaches equilibrium, that enolate that forms on that side will be the major enolate, and then that will be the one that attacks the R group when it's added in its second step to give the other product. And so you have to know the differences between these bases, what base is necessary to use, if you want to control which side of a carbonyl, if there are two different alpha protons on both sides, an R group might be added to. All right, so we can use that idea here to work on this specific practice problem. And so what I'm seeing here is I got to make this molecule from fragments that have 5 carbons or less. So maybe I'll just start counting here. 1, 2, 3, 4, 5. So I can take this piece and I can add these 2 pieces. And that probably makes the most sense. If I count differently, 1, 2, 3, 4, 5. This is going to give me probably the most control over the reaction. So let me explain why that is. So if I start with the structure, what's nice about the structure is I've got 2 alpha carbons. One is very sterically hindered. The other is not. Right? So the more of a difference there is between the sterics on either side of the carbonyl, the more dramatic the difference will be when I use a very sterically hindered base versus not, because of the big difference in sterics on one side of the carbonyl versus the other. So what we're seeing here is we want an ethyl group, 2 carbon group, and a propyl group to be added to the side, carbon 5, that's less sterically hindered. We want to remove these protons and add these groups on. We have to add the groups one at a time. I can't remove 2 protons at once and create a -2 charge. That'd be way too unstable. So what I'm going to have to do here is add LDA. I want LDA specifically because it's sterically hindered enough where it's not going to be able to come in here and pull off this proton because of the steric hindrance of these methyl groups and the isopropyl groups there. That's not going to happen through very low energy transition state. It's not going to happen very often. So I'll add this and expect it to happen here much more often. Then I'm going to probably add the ethyl group because it's smaller. It's not going to create so much steric hindrance to prevent the next group from being added. So I'm going to add ethyl, maybe an ethyl bromide. Oops, I forgot to show the lone pair here. Sorry about that. Right, these electrons pick off the proton, electrons stay behind to form the enolate. And if I add ethyl bromide in the next step, that should attack that primary carbon. There's not too much steric hindrance. Push that out. And I'm on my way. I've added the ethyl group here. I still have a difference now in how sterically hindered one side is versus the other. Right? To pull a proton off a tertiary carbon versus a secondary one, there's going to be a little bit more sterics over here. So I might not get as dramatic a difference here as I was over here, but I still want to use the more sterically hindered LDA to pick off a proton from the side where it won't go through an especially high energy transition state due to steric hindrance. So I make the other enolate, and then in a 4th step, I want to add the propyl group. So I would add propyl with the leaving group, like propyl bromide. That would attack the propyl group, push out the bromide, and give the product. All right, so some other synthesis strategies that are especially useful when it comes to enolate chemistry. And the net result of this reaction is you're going to be able to convert a primary alkyl halide into this structure here, where we have the same exact R group, some primary R group, and it's going to be bonded to a CH2COOH. So we're basically replacing the halide with two more carbons, one of which becomes a carboxylic acid. So here's the method by which we do that. We start with diethyl malonate. We have two ethyl groups. And just so you know, this is malonic acid. It's not an IUPAC name, it's a common name, so I don't expect you to know that this is malonic acid. But if you convert the carboxylic acid groups into esters, you have a diester, so it's diethyl malonate. And this is easily purchased as a reactant. So in this case, I can use an alkoxide base, because what we have here is a proton that's alpha to two different carbonyls. We were talking about that a little bit earlier. If this proton's removed and electrons stay behind, there's extra resonance here to stabilize it, mainly over two oxygens, but also a little bit on the carbon. And so that really helps to stabilize that. So a negative charge spread out over two oxygens in a carbon is going to be a lot more stable than a negative on one oxygen, as we said earlier. So this is no longer equilibrium. We learned last time when we used an alkoxide base on a carbonyl carbon to pull off the alpha proton, normally it forms an equilibrium, so some of the product can attack the reactant. But in this case, we're not getting an equilibrium, specifically because the extra resonance stabilization for that negative charge stabilizes the product enough where the reverse reaction is basically insignificant. So this should shift all of the diethyl malonate reactant into an enolate. And so we can get this enolate to attack this RX. As long as it's primary, it should do an SN2. And so that's what we would do. We would have that attack the RX, push out the leaving group, and we've essentially added an R group there. And if you recall, the product we're trying to make here has a carboxylic acid one extra carbon away from an R group. So we can kind of see that feature here. The R group is one extra carbon away from this. And so the idea next is we have to cleave these esters and make the carboxylic acids and then get rid of one, because this is basically the product we're trying to make. Right, so how do we do that? So first thing, we would cleave these esters by doing a hydrolysis. And so you can use H3O plus in water, or you can use NaOH in water. And we talked in the carboxylic acid derivatives, chapter 21, about how to break up an ester and convert it into a carboxylic acid, right? So either this would be, so if we're using acid conditions, this would be protonated first. Water would come in and push electrons up. The water would be deprotonated, this oxygen would be protonated, electrons would swing back down, push out the leaving group, and then you'd have an OH here, and it would be in the form of a carboxylic acid. If you use base, then the OH minus would directly attack, so this wouldn't be protonated first. The OH minus would directly attack, push electrons up, they'd swing back down, push out the ethoxide group. Then the ethoxide would pick off the proton from the OH that's here. So you wouldn't actually get a carboxylic acid. So if you did this, you would need some H3O plus in the second step anyway. So either of those, you'd want to use excess, because you have to do the reaction on two different esters to convert them both into carboxylic acids. And then what you would do after that is to heat it up. Once you have the two carboxylic acids, heat will cause a decarboxylation reaction. And that's a pericyclic reaction. We talked about pericyclic reactions earlier in the semester. They involve a circular movement of electrons around a ring. So the sigma bond here breaks, swings in here to form a double bond, while this sigma bond breaks, swings over here to form a double bond, and this pi bond breaks and swings out here to form a single bond. So we're actually breaking 2 sigmas and 1 pi. And we're forming, this sigma becomes a pi, this sigma becomes a pi, this pi becomes a sigma. So we're only forming 1 sigma and 2 pi. So we know that sigma bonds are more stable than pi bonds. So the only reason this reaction goes forward is because it produces CO2 as a byproduct, which is favored by entropy, which is why we need heat. And if we increase the temperature of a reaction, it'll shift it toward the side that has more entropy, and forming 2 moles of products versus 1 mole of reactant is going to be favored by entropy. And so the heat really is needed both kinetically to get over the transition state as well as thermodynamically to shift it toward the side with more entropy. So once those electrons move around and we draw in their new positioning, this section here becomes a CO2, and the remaining part of that produces this structure. And then if there's any catalytic amount of acid or base, the enol, which we know is always in equilibrium with the ketone, will tautomerize, and the equilibrium there pretty much always favors the ketone. So that would be the product. So why isn't the second carboxylic acid removed by heat when the first one is? Well, the first one of these carboxylic acid groups helps facilitate the other to leave, right? We can't go through this pericyclic 6-membered transition state if I'm trying to continue to remove the second carboxylic acid group. So that's not going to be, it can't undergo the same mechanism or the same reaction as the other one did with heat, because the one that's already there, which is this one here, facilitates the loss of the other one. So if I have 2, I can do a decarboxylation, but not if I only have 1. So here's a specific example of that process. Again, we're using the base to pick off this proton. That produces an enolate there. Then, in a second step, we're adding an alkyl halide. It's got to be primary, so the enolate can attack it and push out the leaving group. And that's going to produce this. Then in step 3, the H3O plus and heat accomplish 2 things. They accomplish cleavage of the ester to produce carboxylic acids, and they accomplish a decarboxylation of one of the carboxylic acid groups to give the product, which is basically this structure here. That goes through the mechanism we just saw. If you want to put 2 R groups on through this process, you can. You just have to do it 1 step at a time. So you'd need the base to pick off 1 proton, have the enolate attack 1 R group, install that. Then you need another shot of the base to pick off the other proton, and then that enolate will attack another R group and install that. So you can install 2 different R groups or 2 of the same R group. And then the H3O plus in heat cleaves the esters and decarboxylates to give this specific product. There's another version of this reaction that's very similar, acetoacetic ester synthesis. So acetoacetic ester sounds crazy. Basically, the idea here is we have an ester on one side and an acetate group on the other side. Acetate is a common name. It just refers to a CO bond with a methyl. So the difference here is we're not going to have a carboxylic acid. We're going to have a methyl at the end of the structure. Otherwise, it's almost exactly the same. So here's a specific example of that. Instead of starting with an ester on both sides, I only have an ester on one side. But I still have the key feature of this molecule, which is that the alpha protons are alpha to two different carbonyls, so when an enolate forms here, it can be stabilized through resonance over both oxygens. So again, the ethoxide will pick off this proton, electrons would remain behind. Then that enolate would attack here and push out the leaving group. So that would give this. The aromatic ring and this extra carbon between the ring and the carbon that attacked it. Then the H2O plus in heat again accomplishes two things. It cleaves the ester and converts it into a carboxylic acid. Then it decarboxylates. And even though we don't have an ester or a carboxylic acid over here, we don't need that because this oxygen can facilitate the decarboxylation. So let's just take another quick look at that decarboxylation. So I'm going to redraw this one. So to decarboxylate this, it has to rotate so that the OH is in this position, which it would normally do anyway, even though it's not usually drawn that way. But it normally would, because the partial negative of this CO double bond is going to nicely attract the partial positive of that hydrogen and form a nice, strong intramolecular hydrogen bond, right? We're not going to see the molecule exist in a rotation where these two fairly large partial negatives are close together repelling, even though they're not that close. So what's going to happen here is these electrons are going to swing out here. And these are going to swing in to make CO2. And this bond here is going to break and come over here. So again, initially that doesn't necessarily produce a product right away. It produces the enol version of that product, right? This oxygen is picking up a proton. These electrons swing in here to make a pi bond. And so then this would rearrange to give the ketone. And that's under acidic conditions, it's a two-step process. This oxygen would have to swing electrons down, and this would pick up a proton from H3O plus. That would basically give the product with still a proton here on the oxygen. And so then a water would pick that off, and you would end up then with the ketone. So you definitely want to practice these mechanisms. They're not trivial. All right, so we're going to switch gears a little bit and talk about different versions of electrophiles that enolates can attack. All right, so we saw so far that we can get an enolate using the right base. We can get an enolate to attack a carbonyl and do an aldol type reaction. We can get an enolate to attack an R if there's a leaving group attached, and do an alkylation reaction. That's one we were just most recently talking about. We can also get an enolate, though, to attack the beta position of an alpha-beta unsaturated carbonyl. Right, so here's an alpha-beta unsaturated carbonyl. What makes it an alpha-beta unsaturated carbonyl is that we have a carbonyl, and then between the alpha and beta carbons, next to that carbonyl, there's a site of unsaturation, or a pi bond, or an alkene. And what's important about that specific positioning for the alkene is that it's in conjugation with the CO double bond, pi bond, right? So we have full conjugation throughout all four of these carbons and the oxygen. And that conjugation means that when the electrons from the pi bond between the CO double bond shift up through resonance to create this major or significant minor resonance contributor, there's a third resonance contributor where these pi electrons shift over here and put the positive here. Right? So that means now in this type of structure, there are two electrophilic sites. There's this carbon where a nucleophile can nicely attack, and we've seen that already. We know attack can occur on a carbonyl carbon and push the electrons up to an oxygen. And one of the main reasons that occurs is because of the resonance here creating a large positive to attract the nucleophile, but also the induction pulling electrons away creates a large partial positive for the nucleophile to attack. So there's lots of reasons why the nucleophile can come in here and attack this carbonyl carbon. But since there's a third resonance contributor where electrons swing in here to create a positive here, a nucleophile can also attack the beta carbon. Or in other words, we could just show that attack occur directly on the beta carbon and shift electrons all the way up to the oxygen to create a really pretty stable. So let's just imagine that nucleophile came in there. It would look like this. Would have attacked there. Draw like that. Draw like that. The nucleophile would have attacked there. Push these electrons over to form this. And this is resonance stabilized. So really what we have here is if a nucleophile attacks the beta carbon of an alpha beta unsaturated carbonyl, the next intermediate stabilized by resonance, so that can occur pretty readily due to the resonance stabilization that starts to occur in the transition state and is shown here in the intermediate. But that also creates an enolate in itself. And this oxygen can swing back down, and now this site is nucleophilic and it can attack some other electrophile. So what's really nice about these is that there's two sites where connections can be made. A nucleophile can connect to the beta carbon, that then makes the alpha carbon nucleophilic, and so it can attack an electrophile, and you can end up connecting something here and something here. And so that's what we're going to see some examples of and how useful that is. And that is the strategy that's necessary to work with when it comes to solving the synthesis problems that were in today's quiz questions. All right, so what are some of the nucleophiles that we can deal with? Well, we always like to talk about the Grignard because it is a really nice, strong nucleophile. And when you have something that's so strong, in this particular case, it's so strong that it naturally, and there's so much negative on this carbon, that it naturally is much more likely to take the electrons it's sharing with the magnesium and directly attack the carbonyl carbon, because there's a lot more partial positive there than over here. So what this means is the Grignard is so strong that when it attacks there, it does so because of the attraction, and it's just much more likely to collide there, despite the fact that the immediate intermediate that forms is not stabilized by resonance. And it involves a C-C double bond, which is not as stable as a CO double bond. And then the H2O plus would protonate that to give you the OH instead of an O minus. So you got to remember, when you got a Grignard, it's strong enough, it's so much partial negative, it's more often than not going to attack directly at the carbonyl carbon to make an alcohol product. So in the last chapter, we talked about the Gilman reagent, and we said the Gilman is an alternative to the Grignard that's much weaker. As a much weaker nucleophile, it actually will withdraw its electrons from the copper. So we have, let's draw this thing out. The lithium is just a counterion. The copper is negative, but it's more electronegative than magnesium, so it won't allow the R group to pull the electrons quite as much. So we have a significantly smaller partial negative on this carbon of this R group. But it's still somewhat negative, and so it's going to sometimes collide with enough energy to pull the electrons away from the copper, but when it attacks, more often than not, it'll attack here. which will push the electrons up to the oxygen. So the reason for that is because when the R group attacks the beta carbon, you form a resonance stabilized negative charge. It's an enolate. It's stabilized by resonance. Versus up here. So because there isn't so much partial negative, it doesn't have to attack the carbonyl carbon. And the advantage to it attacking here is when it attacks, it produces a resonance stabilized negative charge. And so that happens more often because the resonance stabilization that occurs allows it to go through a lower energy pathway. And so then after you add a proton source, those electrons would swing in and pick off a proton from H3O plus, and that would produce this product. So now this is nice. We have, depending on which reagent we select, we have the ability to deliver an R group either directly to the carbonyl to make an alcohol or to the position that is not alpha but beta to the carbonyl to retain the carbonyl group and install an R group at that position. There are a variety of other nucleophiles that will also do the same thing, where they'll attack the beta carbon because the resulting intermediate is stabilized by resonance. That intermediate can pick up a proton from the oxygen. If it does, it'll usually tautomerize to the ketone form anyway, so rather than showing that way, it's more probably will at least save you some time. Just push these electrons in and have that pick up a proton and go directly there. Why is the nucleophile generally favored to attack the beta position? Because if the nucleophile were to attack the alpha position and push electrons up, the result would be you don't get a resonance stabilized negative charge. So if the nucleophile is very strong, you'll get more of this. If the nucleophile is weaker, you'll get more of this. And that has mostly to do with the attraction between the nucleophile and the partial positive that's greater on the carbonyl versus the smaller partial positive at the beta carbon. So as we're saying, Grignard is too strong. It's more likely to attack the carbonyl directly. The Gilman reagent is much weaker. It's more likely to attack the beta carbon. Oh, what about enolates? Enolates are kind of in between. They're not as strong as a Grignard, but they're stronger than the Gilman. So they often give a mixture of products, which is not really desired. So if we just have a standard enolate, so let's just say, I have just one of these enolates. This one here, it's a simple enolate. Because the resonance doesn't really stabilize the negative a lot, it's still a pretty strong electrophile. And if you add that to an alpha beta unsaturated compound like this, a lot of the product will result from attack here, but a lot of product will result from attack there. So you're going to get two different products. If this carbon attacks here, it'll be connected there. If it attacks directly at the carbonyl carbon, you would end up getting the result of that attack in the end. And if we get a mixture of these two products, then it's a real pain because we got to use column chromatography or some other technique to try to separate them from one another and isolate the one we actually want. We're not going to get a high yield of it because we're also converting a lot of our reactants into the other product. So we want to avoid that as much as possible. So as we were saying, if the nucleophile is too strong, we'll get a lot of it attacking the carbonyl directly. So if we want this to work, and we want to avoid a mixture, we need to stabilize the enolate so it's not so unstable and so strong, and that will decrease how often it attacks the carbonyl carbon and make a much higher yield of it attacking the beta carbon. So how do we stabilize an enolate? We give it more resonance. And that's exactly what we're showing down here. So doubly stabilized enolates are stable enough that they'll almost always react at the beta carbon rather than at the carbonyl carbon. And so that's the idea here. I use a base to pick off a proton from one of these doubly stabilized enolate sites. And when that picks off that proton, the electrons will remain behind there. I'll form an enolate, and that enolate stabilizes through resonance with both oxygens. That stabilizes it enough where there isn't really that much negative at this carbon. So when I look at the resonance hybrid here, there's only a very small negative, so it's not that strongly attracted to the positive here. And it will be more likely to attack this site because that will be more stable as the electrons swing around to create a resonance stabilized intermediate. So let's just draw that real quick up here where I can draw it small enough. So this molecule then would have attacked this beta carbon, and there's still a methyl on that carbon. And then these electrons would swing over here and push those up to the oxygen. So that would be the next intermediate, and then when H3O plus is added, these electrons would swing back down, and this would pick up a proton, and that would give you the product. So if my enolate is doubly stabilized, I can get a pretty decent yield of a pretty complicated structure. And I'm very quickly building up this carbon skeleton to make it interesting and complex and maybe get it closer to the complicated structure I maybe need to make as a pharmaceutical or some other interesting property that the chemical might have. I'm getting two large fragments and getting one to attack the other and forming a new carbon-carbon bond here in a pretty controlled way. I end up getting carbonyl carbons that are 1, 2, 3, 4, 5 atoms away. It's a key feature of this reaction. And so this has a lot of synthetic utility, and we want to explore a few more options here. So this slide shows how there are a variety of doubly stabilized nucleophiles that are like enolates. The Gilman reagent is one of them. It's not doubly stabilized, but it's relatively stable and a relatively weak nucleophile. So these are the relatively weak but strong enough nucleophiles that we need to attack one of these beta positions. So some nucleophile that's got some resonance stabilization, either with a nitro group or a CO double bond on two sides or a Gilman reagent, those are weak enough where whichever one I select, it should come in and attack the beta proton, or sorry, not beta proton, beta carbon to push electrons up to the oxygen to give a resonance stabilized intermediate. And so this is called, in a larger sense, the Michael addition. In the Michael addition, you have a relatively weak nucleophile attack the beta carbon of an alpha beta unsaturated carbonyl compound, and then depending on the other groups around, that gives you the variety and synthetic, variations that might be useful depending on the specific molecules you select to connect together. So there's a fair amount of utility there, a variety of different options. So let's just look at this option here as an example. What would happen if so first of all, I would have to make this Michael donor. And so I would start with this compound and add a base, right? Even NaOH or KOH, so it could be an OH minus, it could be an OR. LDA is kind of overkill. I don't need a really strong base here because once one of these protons is picked off, there's going to be a resonance with the nitrogen, as well as resonance with the oxygen, as well as resonance with the carbon. So all that resonance stabilizes the negative enough. I don't have a very large partial negative on the carbon, and so I expect it to be more likely that it would attack the beta carbon rather than the carbonyl carbon here and push these electrons up to the oxygen. So now this carbon will have attacked this one, so they'll be connected. So we'll just number these. I don't want to lose anybody. So carbon 2 here would have been connected to this carbon. So this would be 2. We have 1, 3. These pi electrons would shift over between 3 and 4. And the electrons would shift up here onto this oxygen. In this case, because there's a leaving group, I would expect those electrons to potentially swing back down and push out that leaving group. But if that happened, then I would have a ketene. If these electrons swing down in here, push out that leaving group, that would produce a ketene, which I'll just quickly show and point out it's not going to be very stable. These cumulated pi bonds we talked about back in chapter 17 aren't very stable, so I wouldn't expect that to occur. Well, what I would expect to occur is the product would accumulate in this form since it's stabilized by resonance until an H3O plus is added. These electrons will swing back in and pick up a proton from the H3O plus. So I'm running out of space, so I'm going to take that over here and draw what the product would look like. Right, so these products, it's kind of a pain to draw it all, but it is nice to be able to make something that's got a lot of carbons and they're connected in a very specific way from relatively small, easily purchased reactants. So if I give you reactants, you should be able to recognize when they're likely to undergo a Michael addition, draw the mechanism if asked, and also predict the most likely product that forms. Another similar reaction to the Michael addition type reaction we just saw is the Stork reaction. And the Stork, instead of using one of these Michael donors as a nucleophile, it uses an enamine as a nucleophile. So we have to reach back to chapter 20 where we talked about making enamines, and enamines are formed from a secondary amine and a ketone or aldehyde. So if you recall that mechanism, what happens first is the ketone or aldehyde picks up a proton, then that makes it much more electrophilic than it would normally be. So the secondary amine can attack, push electrons up there. And then we saw how, each one of these steps is reversible. And so, what could happen is the oxygen could swing back in and push that back out and go back. And then this oxygen could be deprotonated and it could go back. Or it could go forward if Another molecule of the amine picks off this proton. You form a carbanolamine. That could go back if the nitrogen picks a proton back up, but sometimes the oxygen could pick up a proton, which makes a good leaving group. So then the nitrogen can shift those electrons in and push that out. And as we said before, that creates an iminium ion. But that nitrogen's pretty unstable, so another molecule of the amine, the secondary amine, would end up picking off this proton to push electrons in and up to the nitrogen, and that gives the enamine. So what's interesting about an enamine, that was all from chapter 20, is that the lone pair of the nitrogen does contribute through a significant but minor resonance contribution to putting some electron density on this carbon. And if we look at this significant but minor contributor, it's kind of like an enolate. Right? But this is a minor contributor, so the amount of negative on this carbon is very minimal. And so this is actually just right for us. If we want this carbon to have a very small participation of lone pair existing there, and a very small amount of partial negative, but enough to make it attack an alpha beta unsaturated compound, we can make that work, or that will readily happen because it's not such a strong nucleophile. There's not much partial negative here. It's not going to attack a carbonyl, but it might attack the beta site of an alpha beta unsaturated carbonyl, right? So here we're showing the similarity between the enolate and the enamine. Both have a resonance contributor with a negative on a carbon, but in this case, since there's a full negative on the structure, there's a very large partial negative here if we were to look at the resonance contributor. Very large partial negative on the carbon, not as large as the oxygen, but this is a pretty strong nucleophile, and we said it's too strong. It will start attacking directly at the carbonyl carbon rather than the beta carbon. And that will do like an aldol type reaction that we talked about earlier in chapter 22. But the enamine, because this is such a minor contributor, because the major contributor has no charge at all, when it attacks, it's much more likely to attack the beta carbon and go through the resonance stabilized intermediate. And so it acts as a Michael donor, a weak nucleophile that will attack the beta carbon of an alpha beta unsaturated site rather than directly at the carbonyl carbon. And so that's what we see. So if we make an enamine and add any of the Michael acceptors from this side of this slide, any one of those, the enamine should be able to attack the beta carbon, push electrons up to the oxygen. That produces this intermediate here. And then the H3O plus, in this case, serves two purposes. The one we've already seen in these Michael addition type reactions, where the electrons swing in and this pair of electrons picks up a proton to reestablish a CO double bond. But also the H3O plus in water are the conditions we need to remove the iminium or imine functional group and replace it with the CO double bond. So this is really a great way to produce CO double bonds that are 1, 2, 3, 4, 5 atoms apart from one another. Right, so the H3O plus in water both hydrolyzes the imine, or in this case iminium ion, to the ketone, and it also provides a proton for this enolate to pick up And that's how I get two CO double bonds at that specific distance from one another. So when you're looking at syntheses for the next exam next week, well, keep in mind, looking at these patterns, keep in mind the Stork reaction if you end up producing carbonyls that are 5 carbons apart. So let's use it to make one here. So what am I looking at here? I see 1, 2, 3, 4, 5. 5 atoms apart between my two CO double bonds. And so I can make this pretty large, pretty complex carbon skeleton by making carbon 2 attack carbon 3. This is the bond I'm going to form. And I could also make carbon 4 attack carbon 3. So there's really 2 different disconnects here. So let's look at them one at a time. So let's look at this disconnect, working backwards. What I would do here, working backwards, is to disconnect here. I start with this 5-membered ring. I would first add any secondary amine. So maybe I would use diethylamine and a little H plus as a catalyst. That would convert this into an enamine. Then in a second step, I would add the rest of the structure. So we know the enamine is slightly electrophilic from this carbon, and we want it to attack carbon 3. So the structure we're going to add there in step 2 is going to have a double bond between 3 and 4 that's in conjugation with the CO double bond. And then I just need to put the right methyl groups on where they belong. That way the nitrogen can swing its lone pair in, and this can attack here, pushing these electrons all the way to the oxygen. So I should probably number these. So let's call this 1, 2, 3. Oh, we already have it numbered. Let's call this 1. Keep the same numbering. 2, 3, 4, and 5. So this is carbon 1 and this is 2, and 2 attacks 3. 3 has a methyl group. 3 is connected to 4. The pi bond shifts between 4 and 5. 4 has a methyl group. 5 has a methyl group. And electrons swing up to the oxygen that's on 5. So that produces this intermediate. And then, so this would be step 2. So then in step 3, I just add H3O plus and water. That converts the iminium ion into the CO double bond, and it allows electrons to swing in and pick up a proton to reform the CO double bond there. So that's one option. Let's look at the other option. So in that option we just looked at, we made this carbon the nucleophile and this carbon the electrophile. This carbon was nucleophilic because when we make the enamine here, there's a pi bond that can reach out and connect to the electrophilic site. So the other option would be to make this one the enamine, which would mean its pi bond would be here and it could come out and connect to this electrophilic site. Nucleophilic. So if we're working with it this way, our disconnect would be there. And so we would start with this ketone. renumber these. This time I'm going to number from this direction, just to help make more of a difference there. So now I've got carbon 2 there. And the first thing I would do is add some kind of secondary amine, like diethylamine, and a little acid catalyst. And we said when we form the enamine or imine, we want the pH to usually be around 4. That produces enough H plus to protonate here and induce the nitrogen to attack, but not so much H plus that all the nitrogens have picked up H pluses and they can't be free with a lone pair to attack as a nucleophile. So that should form the enamine there. When that enamine forms, it'll look like this. Oops, not like that. There'll be a nitrogen there. Oops, and also won't have a double bond. Sorry about that. The enamine will form a pi bond between 1 and 2 because it's more substituted with carbon groups. So after this stage, what I would end up with would have a pi bond here between 1 and 2, and the nitrogen would have the 2 ethyl groups there. So that's the enamine that would form after step 1 here. So then in step 2, I'm going to add the rest of this. That's a big chunk, so maybe I would go with the first route we talked about instead of this if it were cheaper and this molecule were maybe expensive or something. But the key here is I have to put a pi bond between 3 and 4 if I want carbon 3 to be electrophilic so carbon 2 can attack it. So I'm going to draw this with a pi bond between 3 and 4. And there's still a methyl group on 3. So now these electrons can swing in. This pi electrons starting from carbon 2 will reach out and connect to carbon 3, pushing electrons up to the oxygen. Very similar to the last example, we just disconnected in a different spot. So that would produce carbon 1 with a methyl and a positive here. Carbon 2 also has a methyl, and carbon 2 is now connected to carbon 3, which also has a methyl, and 3 is still connected to 4. The electrons swing in between 4 and 5 and up to the oxygen on 5. And then, right, so this would be added in the second step, and then in the third step, you'd add H3O plus. And again, that would protonate, not the oxygen. The electrons would swing in, and this pair would pick up a proton, which is how I get another proton on carbon 4. And then the iminium ion would be hydrolyzed with H3O plus and water as well to produce a CO double bond. If you want to see that mechanism, let me know. I can show it to you sometime. But we did talk about that in chapter 20. You can also do these reactions in a cyclic manner, but I'm not going to test you on a cyclic example of a Michael addition or an aldol addition, so probably skip over that for now. So just a couple hints to help you when you're dealing with a synthesis question like the ones on today's quiz or anything you might see on an exam. As we said, one sign that you want to use the Stork enamine reaction is if your product has carbons, carbonyls that are 5 carbons apart. We saw a couple examples on how to do that. The aldol or the Claisen, the aldol usually gives an OH 3 carbons away from a CO double bond. The Claisen usually gives a CO double bond 3 carbons away from another CO double bond, right? So noticing which functional groups are present and how many carbons there are between them. If you practice that, that can be a really helpful way in determining which set of reactants or which of these reactions we're working with is going to be useful to you. There's also another strategy that actually combines two of these reactions together. And this strategy involves a weak nucleophile, like a Gilman reagent, or the enamine we just saw in the Stork reaction, or a doubly stabilized enolate. So any of these Michael donors that are relatively weak nucleophiles, what's nice about these, we'll just look at this one where there are two ethyl groups, is they're weak enough that we expect them to attack the beta carbon of the alpha-beta unsaturated carbonyl, push electrons up here. And what that produces, as we were saying initially, is an enolate. Because when the oxygens swing up here to give a negative, that's in conjugation with the pi bond that forms right here. And this alpha group comes in here. Since a weak nucleophile, any Michael donor we saw, attacking the beta carbon produces an enolate, what we've been doing so far is then adding H3O plus, because we have the enolate move back in, and then this picks up an H3O, a proton from an H3O plus. But it doesn't have to be protonated. It can also connect to an electrophile. So this is like a 1-2 punch. You have a nucleophile attacking, making a new carbon-carbon bond here. That produces an enolate that now is a nucleophile. And so an electrophile can be added, and that's the second punch where the electrons swing back down and connect to a primary or methyl with an alkyl halide. And so we can really overall install two carbon groups on adjacent carbons across that pi bond. So it's a really powerful way to increase the connectivity of carbon groups really in kind of like one step, because it's really two steps, but it's one pot. We put one reactant in, let it fully react, then add the second reactant right into the reaction, because it's ready to go to pick up that methyl group. So that's a really nice way to install more carbons to the structure of your molecule. And so here's an example of that being played out. So here I can see I'm trying to make this compound here. So we'll just number these real quick. So I got to add 6, 7, 8, 9. I got to add 4 more carbons. And I want to get this to connect 5 to connect to 6. Right, so what I need to do here is to make 5 nucleophilic. So it'll bond to 6. So how do I make 5 nucleophilic? I have to add a base. In this particular case, if I add a small base, it might pick this proton off, because the enolate will be more substituted with carbon groups. So I need specifically LDA, something like LDA that's very sterically hindered to pick off this proton to form the enolate on the right carbon. Once that forms an enolate, I want to get it to attack carbon 6. So I'll make carbon 6 electrophilic. 6, 7, 8, 9. So I need a 4 carbon electrophile for this enolate to attack. And this is a pretty strong nucleophile, because it's not doubly stabilized through resonance. It's only 1 oxygen to help stabilize that negative charge. So I expect that to come directly into the carbonyl. This is an aldol type reaction, and it'll push electrons up to that oxygen. And so that will initially produce something that looks like this. So I'll have, this would be carbon 1, 2, 3, 4, so that's already 2, 4, and 5. So I've got 1, 2, 3, 4, and then 5 is connected to 6. And 6 is still connected to 7, 8, and 9. So after I add that electrophile for the enolate to attack, the third thing I would do here is add some H3O plus and heat. Because what I can see is I'm making this pi bond between 6 and 5. That means I need to make this oxygen a leaving group. So the heat will help drive that forward by entropy. So what's going to happen here is the oxygen is going to pick up a proton. It won't be charged anymore. It's going to pick up another proton, and that will make it positive. And now it's a great leaving group, so it will leave. And that will produce a carbocation. And then this proton would be picked off by water that the H2O plus will be dissolved in to form the pi bond, specifically in the position where it's conjugated with the other pi bond, right? Because we know the conjugation allows for a molecular orbital to stabilize the pi electrons better. So that would give me this initial product. So that's a 3-step synthesis to get from here to here. So then to get to the final product down here, I can see when I count the carbons up, that I need 2 more carbons here and 4 more carbons here. An ethyl group and a butyl group. And right now, if I can get an ethyl group to attack carbon 6, I can get it to install there. So I'm going to use the Gilman reagent with ethyl groups. The ethyl group from the Gilman reagent will come in here, push electrons up to the oxygen. That will form an enolate. So they'll swing back down in, and then that pi electron pair will have to attack a butyl group. So what I want is a butyl group with a leaving group like a bromine. Right, so just show that. So the ethyl group would pull its one of these ethyl groups would pull its electrons away from the copper, attack here, and push these electrons up to the oxygen. The ethyl group would come into 6, so now it would be connected there. Then this is an enolate. So to make the product, the butyl bromide or butyl chloride or butyl iodide would be used. And these electrons would swing back down and attack it from there to push out the leaving group, which would give the product. All right, so that leaves the last 2 slides here. Even though we're out of time, we'll just go over these last 2 quiz questions for today's lecture. And they draw on all these strategies. And what I can see over here is there's a lot of extra carbons compared to what I started with. So this is not going to be a short synthesis. I've got to get these carbon groups to connect here. It's going to be very similar to the last problem we looked at, though. So what I have here is an alpha carbon that's alpha to 2 different CO double bonds. So really any base I want will pick off one of these 2 protons. So I'm going to use an ethoxy, and that's probably the best choice here because I do run the risk of that ethoxy also attacking here and pushing this out. But if I don't want that to be pushed out, because it's there for a reason, I can use an ethoxide group because if it does come in and push that out, I still get the same structure back. So this will allow me to pick off this proton, make that into an enolate, and then I can see that carbon, I need to replace both these hydrogens with other groups. So initially, I'm just going to replace that with an ethyl group, this one here. So in the second step, I'm going to add an ethyl bromide. So to point out, after those first 2 steps, the first one picks a proton off and makes an enolate. The next one supplies an electrophile for the enolate to attack with the leaving group to leave. So that installs that ethyl group right there. Then now I want to get rid of this. It's not there in the end. And so to do that, I'm going to employ the strategy we talked about before, which is to use H3O plus and heat. The H3O plus will convert this ester into a carboxylic acid group. And then since there's another CO double bond a couple carbons away, that will facilitate the decarboxylation reaction we saw earlier today and get rid of that carboxylic acid group. And so that will be gone and replaced with a proton from the H3O plus. Now I've got two different alpha carbonyls. One's more sterically hindered than the other. So I want the reaction, this methyl group over here isn't changed, so I don't want to form an enolate there. I want the enolate to form on the other side. So I might use a hydride. We saw the hydride with its lone pair is small enough to get into the less sterically hindered side, and it is weak enough where it will produce an equilibrium, so the enolate will form on the more thermodynamically favored site, where the pi bond's more substituted with R groups. So that will form an enolate over here. And then I want to get some of this to connect here. So the next step I'm going to add is a aldehyde. I'll just point out, you could also use NaOH here. It's not strong enough to convert all of this ketone into an enolate, but it would produce a little bit into an enolate. And since this doesn't have an alpha carbon, it's safe to add all that together because there's only one alpha carbon that can form an enolate other than this one, where it won't form because it's not as stable to form the enolate on that side when there's no R groups to stabilize the pi bond. So this would come in here and attack. Pushing electrons up. So I'm basically utilizing the aldol reaction here. Then I'm going to add more H3O plus and heat. That's going to protonate this twice, make it a leaving group, and then this proton here is going to be removed to push that leaving group out. And that will make a pi bond here. And now it's set up for the Michael addition. I still need to add this ethyl group and this methyl group. And I can do that in two quick steps. The ethyl group can be added as a nucleophile. So I would use that as part of a Gilman reagent. The ethyl group would come in here. Basically attack there and push electrons up to the oxygen to form an enolate. Then they would swing back down and produce a lot of negative on this carbon, and then the methyl group could be added in the form of methyl iodide or bromide or something, and that carbon would attack that methyl group. Right, so that would go through one more intermediate where the ethyl group's connected. Those electrons will swing back down and attack the methyl group to push out the iodide, and that would give me that methyl group there then on that carbon. So I would probably not give you a synthesis on an exam that's quite that long, but that does take advantage and illustrates a lot of the reactions we talked about today. So it's a great example to illustrate those specific reactions. Here's another one, very similar, slightly different, obviously. In this case, what I'm seeing initially is that I've got these two carbon oxygen double bonds 5 carbons apart. And so that's either a Stork reaction or a Michael addition. So if I have a situation where I can form an enolate that's stabilized by 2 CO double bonds. I don't need to worry about the Stork reaction or forming an enamine. I can just add a base and pick one of those off. So the same first step here as we saw in the last one. I'll pick off one of those protons and form an enolate. So on this carbon, I still have one hydrogen in the end, but I want to install an ethyl group. So now's my opportunity to do that because I picked one of these protons off to make the enolate. And so I would add an ethyl bromide or iodide or something like that, so that that ethyl group would then be installed at that carbon. So then the next thing I want to do here is to get rid of this because it's not there in the end. So we'll do the same thing we did in the last example. YH3O plus in heat. That'll cleave the ester and make this into a carboxylic acid and decarboxylate it through that mechanism we saw. And so that should produce this. Basically, we're starting with the same first couple steps we looked at in the last example. So now I want to install the other ethyl group on the other side so that this ketone will be symmetrical. That way, when I go to add the other carbons, it doesn't matter what side it adds to because they're equivalent. So now I want to recognize that one side's more sterically hindered than the other. And so if I want to form the enolate over here and install the ethyl group on the other side of the carbonyl right here, install that ethyl group, I can use LDA. The more sterically hindered base should form the enolate on this side, and then adding another ethyl with a leaving group would cause that enolate to attack that ethyl group and install the ethyl group on that side of the carbonyl. So now these two alpha carbons are equivalent. The two R groups on either side of the ketone are equivalent. So now I just have to get one of those to form in a way where it can connect to the other part of that. And now I'm noticing actually I do want to use the Stork reaction, because if I try to form either of these into an enolate, it's not going to be extra stabilized with extra resonance, right? When I form an enolate here, it's only going to be stabilized to resonance with one of these oxygen, with one oxygen, not two. And that's too strong of an enolate to get it to attack this beta position of this 4-carbon group. So I want the Stork reaction here, and so that means I'm going to need to add a secondary amine with some acid catalyst. That will convert this into an enamine. That is going to be a little bit nucleophilic from that site. So if I add the rest of the 4 carbons as an alpha beta unsaturated compound, this nitrogen would push its electrons in. These would swing out here and tack there and push these electrons up to the oxygen. So that would form this. So then this carbon here is the one that attacks. So be connected to the rest of that chain. And then after that step, the last step would involve some H3O plus and water. The H2O plus and water would cleave this and convert it back into a carbonyl. And it would pronate this carbon here as these electrons swing in, and this carbon here picks up a proton, so it has 2 protons on it. All right, let me know if you have any questions about any of that stuff anytime. I'll definitely be giving you all some comments on your quiz answers. Most of your groups have a fair amount of bonus credit from doing especially well on previous quizzes, so if you don't get the full 4 points out of 5 today, I don't feel too bad about that. I know those were especially challenging quiz questions. But this is a section where you definitely want to do some practice, because noticing some of these patterns in syntheses and working through the mechanisms definitely is going to take some time and effort. So do as much of that practice as you can. Let me know if you have questions about it. And on Wednesday, we will get into chapter 23, which is our last chapter of the semester that we're going to be covering. It's about amines. We've already seen a few reactions that amines undergo, but we want to look at how to produce amines and some of their other reactions. So we'll be focusing on that on Wednesday.